but it's actually, yeah, I'm just in my own office, so I'm in my own home office. So it's a pleasure talking to you anyway. I gave this a very similar talk to this a couple of weeks ago, so I did not see any duplication in the audience, and that's good. But if you did attend the previous one, like about 2 weeks ago, then I apologize for the duplication. It's the same material, the same paper that I'm talking about. So the motivation for this project that I'm going to tell you, it's not just myself, it's a whole bunch of people. I'm going to introduce them at the end. The motivation for the project is trying to understand how to decode what a brain is doing or a network of neurons is doing. And in short, basically what you're looking at is a directed graph, which is encoding the neural structure of a brain or of a portion of a brain. And you want to classify spiking activity, which is what we call binary dynamics on that graph. So that's the idea. Now, a brain, as probably you all know, is made out of neurons, and you see a picture of a particularly nice neuron here in this picture here. And neurons are, you know, the picture I just showed you looks a lot like an actual neuron, whereas in this schematic, what you see is the very intricate structure, the very intricate internal structure of this tiny object, which is basically the way in which the neuron connects to all other neurons and receives connections from all other neurons. These are the synapses. These are the synapses. Every neuron has a few hundreds and sometimes even a few thousands of them. And they are very sophisticated chemical connections which enable neurons to do jobs that are much more than just looking at just connecting, you know, from one cell to the next one. Okay, we don't really understand what, or rather we cannot predict whether a synapse, a connection, is going to respond to a stimulus and basically move the stimulus further or not. And this is what we refer to usually as the noisiness of a system of neurons, okay? Whether it's predictable if we knew everything about everything that is happening there or not, that's a question. But we basically, when we look at the operation of a neural system, what we are seeing is very, very noisy responses to even the same signals that we are sending in, okay? Which makes the task of trying to classify neural activity very, very difficult one. Right, so how do you encode, generally, how do you encode neuronal activity? Basically, you encode neuronal activity by, the easiest way to do it is by what is called a raster plot, which is an example of which you see here. It's basically looking at the firing of each neuron as a point on a straight line, straight horizontal line. And so these patterns that you see here are basically the firing of neurons. Every dot corresponds to a neuron firing once, okay, along a horizontal line. So here you have, I think, 310 recordings of incoming stimuli going into the system, into a system I'm going to describe shortly. And very similarly, you can also read the response of a system of neurons by a raster plot. And here you see the response, doesn't correspond to what I showed you before, but you see the response of the neurons, every line and every horizontal line here in each one of these 5 charts. Every horizontal line has a number of dots on it. Each dot means a neuron has fired at this particular time point. Okay, this is the raster plot. Now the point is that if you look at the raster plot, it doesn't make any difference to the actual data that's being presented there in what order you organize your neurons. Okay, so in other words, if I took my neurons in each one of these rectangles and reorganize them in totally different order, I may get a different picture, which nonetheless corresponds to exactly the same activity. In other words, this is invariant under the action of sigma n. The data is there, that particular property, it's nice because you don't have to worry about the order. But on the other hand, to classify or to try to understand what's going on using raster plot is very, very difficult, more or less impossible. you know what the neurons are doing, like they are active and how active they are, but you don't really see much more beyond that. Okay, what we are playing with for the past few years, one of our major sources of data is the blue brain reconstruction of the neocortical column of a rat. And we've done various bits of work on this and we're still doing. But the most important fact to know about this reconstruction is that it consists of roughly 30,000 neurons with about 8 million synaptic connections. And most importantly, you can simulate activity. You can trigger activity and you can record a response on that system, which is as close as possible to an actual tissue without actually being one, it's just a computer. So we think in this work, we think about networks of neurons as directed graphs. And, here's an example of a very simple one, just to demonstrate that when we think about directed graphs, we want them to be simple. And simple here means that you allow bidirectional connections, but in any direction, there's only one connection allowed, and no loops. Okay, so that's the type of graphs we are looking at. And to talk about the subject of this talk is binary dynamics. So what we mean by binary dynamics is the following. A binary state on a digraph, a directed graph, is just an assignment of binary values to each one of the vertices. Very, very simple. Binary dynamics is some sort of a one-parameter family of binary states. But in practice, really, it's not really a one-parameter family because this is discrete information. So what you're looking at is a time series of binary states, some time series of binary states on your network. Okay? And so the problem that we are trying to solve is the following, generally speaking. And this is not only in neuroscience, but generally, whenever you have any setup which will give you binary dynamics, you can think about this approach. So you're presented with a large family of, let's call it D, of binary dynamics functions on some fixed large digraphs. So the understanding what's going on there should be complicated. Then you're given a bunch of labels. I'm going to work here with 8 labels in the end. So given a bunch of labels and a function that associates with every binary dynamic function, with every sequence of binary states, a label. Okay, and assume that if you to look at every letter in this label, its inverse image in the family of functions carry some resemblance to each other. For instance, in the neural system, they come from the same stimulus to the network. Okay, like I said before, the neural systems are usually very noisy. So, but if you insert one particular stimulus, you expect to get not a single identical response every time, but a family of responses which somehow should be related to each other. So there should be some resemblance. And the fourth assumption that you're making is that it is noisy. In other words, you won't be able to just look at the picture, look at the firing patterns, and distinguish what the label is. Okay, so more than that is required. And the task is to find an efficient method that will turn binary dynamics into machine learning digestible data set. So we can train some machine learning algorithm and then try to read off what the system actually did. Okay, so that is the project. All right. So of course we are topologists. So what do we do when we have a problem, any problem of any kind? Hopefully not a problem in life, but something in science. We apply topological methods. So we want to turn the brain into a topological space and then extract information from the resulting object. All right. And I try to give this picture the really psychedelic color so that, if you can see some structure there, but anyway, not sure you like it or not. I thought it's nice. Right. So what sort of tools are we using? Well, there are some familiar constructions in combinatorial topology that you can associate with the directed graph or even with the undirected graph. And I'm going to mention a few. For instance, the neighborhood complex, the flag complex or its dual, the independence complex, You can look at the category generated by the graph and the nerve. You can look at neighborhoods. I'm going to talk about those, and click communities, or you can talk about the directed flag complex and also a relatively new object that we came up with, which we call the flag ternoplex. And these typically yield things like abstract simplicial complexes, ordered simplicial complexes, or semi-simplicial sets, which are, of course, all familiar tools in the toolbox of an algebraic topologist. And with those, you can go ahead and do some analysis if you're lucky. Okay, so I want to review a few of these things. So the directed flag complex is a very simple object. You have a directed graph and you look at its directed clicks. Okay, so directed click is one that it's a click, so it's a complete graph on a set of vertices, where the orientation of the edges gives you a linear order on the vertices. Okay, if you have one of those, like you see in this picture here, then you associate with it the simplex of the appropriate dimension, and if not, then you do not do that. Okay, so this is the directed flag complex. It's an ordered simplicial complex. In other words, if you think about it abstractly, it's an object whose simplices are ordered, finite ordered sets, which is closed under subsets, under ordered subsets. And we use that in our first collaboration with Blue Brain. We use that, and I'm going to mention this again in a bit. Another combinatorial construction which we used recently, and I'm going to talk very little about today, is the tournaments. So tournaments are also clicks in a directed graph, but now we take into account the direction of edges, and we don't only look at those that give you a linear order. In fact, we don't look for any order at all. We look at all of them together. The advantages of doing that is, first of all, you get a lot more of these objects, a lot more clicks than you had before. The second thing is you can associate with a tournament, you can associate an invariant we call directionality, which will allow you to define a filtration on your space, on the resulting space. I'm going to describe the space in a second, but the point is that these actually have a tournament has, and it's isomorphism type, obviously, but there's an invariant called directionality that allows you to do more with an object constructed from those tournaments. And the objects are called ternoplexes. So what is a ternoplex? Well, basically, just like you do with simplicial complexes, it's a finite collection of tournaments which is closed under taking faces. So in other words, if you have a tournament in particular is going to be a clique. So every subclique is also a tournament, and so it has to be closed under taking faces. And you can give it a structure of a similar simplicial set by choosing, by looking at n simplices being the n+1 tournaments, so the tournaments on n+1 vertices. You fix the total order on your ambient set, and that allows you, in a fairly standard, straightforward way, to define face operators, which gives you the structure of a semi-simplicial set, and you can realize that and get a topological space out of it. And I gave you a reference here for this project, which is about to be published in Journal of Applied and Computational Topology. So,
would you mind going back? And I assume this is an important concept for your talk. And could you go back one slide and to get the ternoplex and tournament?
Yeah,
right?
Yeah.
Sorry, I guess I meant one further, where you actually define. So I'm not sure whether I understand why is this now a regular tournament?
Why is what?
Sorry, what is an N tournament? You said it's a complete.
So an N tournament is basically
is it directed or just?
It's directed. Yes, it's directed. So okay, it's a directed graph, which, if you forget direction, it's a clique.
Right. Yeah. Oh, I see.
It's a directed complete graph, right?
So the underlying undirected graph is complete.
Yeah.
I see. Okay.
Yeah.
Thanks.
Okay. So those things. I mean, the direction allows you. I think I have other talks about that. And there's the paper, but the direction actually allows you to do a filtration on the complex that you build out of them. Okay. Right. So, so I told you what a turnoplex is, and in fact, if you have a directed graph, you can look at its tournaments. Okay, you can look at all the tournaments in the graph and glue them together in the obvious way. Basically, you know, every face is again a tournament, and you get what we call the flag turnoplex. Okay, which you can then filter and get a filtered space where you can do persistent homology. And so we apply these two methods, these two constructions, to the data set that I showed you before. In our first collaboration with Blue Brain, we noticed that, well, we used this, you can see here, 9 different stimuli that we inserted into the circuit that come in 3 different families, denoted by S5, S15, and S30, and each one of them in 3 variations. And then we measured the response of the system, and we did something. I mean, here, what you see here, for instance, is the Betty1 graphs of the responses, and the Euler characteristic, and Betty3 in here. And here we graphed Betty1 against Betty3, and we got these patterns. But this was a very, I mean, you can see that there's a difference, but and practically all simulations behave in a characteristic way, in the sense that they kind of, the Betty1 against Betty3 did this swoosh loop, you know, this loop according to time, but it failed miserably of being classification, even of these 3 families. Okay, so we couldn't actually get a classifier, but we saw some characteristic behavior, which was interesting. So, not being satisfied with that, we decided to look at tournaments, because maybe there's more information there, because you can use persistent homology. So we took, instead of looking at the entire circuit, we only looked at layer 5. So those that the neocortical column, as the neocortex, is divided into 6 layers. Layer 5 is the layer where most of the activity is happening. And so we did 2 things. One, we looked at the turnoplexes, the flag turnoplex. We devised an algorithm which used the persistent homology to vectorize the response of the activity from those 3 families of stimuli. And then we applied a k-means clustering algorithm to the result. We did the same thing with respect to the Betty numbers of the same data, just the Betty numbers of the same data that result from the directed flag complex. I'm not describing the algorithm, so I'm going very quickly, because this is not really the subject of my talk. But here are 2 experiments which try to classify the data into 3 families. That's all, not all 9 of them, not all variations, but only 3 families. And what you see here, the top chart, is basically how, using turnoplexes, managed to almost separate almost perfectly the 3 families, whereas from the same data, just the directed flag complex did miserably bad. As you can see, 15 and 30 are completely identical, and 5 is pretty consistently not classified correctly. So, so that showed us that, you know, if you add structure, you can actually get better classification. But nonetheless, when we try to apply the turnoplex method to the data I'm going to describe next, the result was, again, quite pathetic. And so we want to do more. And that's where I'm getting to the subject of the talk. So what was the problem that we observed, kind of more like guessed than observed? The point is that if you look at the entire network and what it does during a stimulus, how it reacts to a stimulus, it's too large. Not only in the sense of too complicated to compute, but also just the signature of signals is just too similar. Everything starts firing, basically. So you can't, I mean, it's very difficult to use the entire system. If you look at single neurons or simplices and you build symbolic complexes from them, then the signature of the signals is too noisy. Yeah, so it's like you look at the raster plot, for instance, it's too noisy to see anything. So the idea is, how about using a collection of subgraphs that could perform as computational subunits, not single neurons, not simplices or cliques, and certainly not what is very common in neuroscience, to use 3 or 4 neuron motifs, but something much larger, considerably larger, that could be thought of computational subunits, larger than simplices, but much smaller than the entire circuit, and use those. And we did that project in 2 papers. One of them, well, both of them are one archive, one bioRxiv, both being considered for publication now. And that's what I want to describe next. So the data that we are trying to classify is the following. We have 8 different stimuli generated for us, and then injected into the Blue Brain Project microcircuit in a random sequence. There are 4,495 of them in 8 families, random sequence, okay? And basically what we want to do is to predict the sequence. So train a machine learning algorithm on standard 60% of the data, and then try to predict the rest, okay? And as I said already, first of all, we tried to use our previous mechanisms to do that, and the results were hopeless. I mean, it was too messy. One reason for that is because these stimuli are much more lifelike than the ones we used before. So they're sparser, they're noisier, and they're much more difficult to predict. So the idea is the following. Suppose you have a way of selecting a collection of meaningful subgraphs. So you need to select subgraphs, right? Like computational subunits, subgraphs. Suppose you have a meaningful way of doing that. Then you're given binary dynamics. So we can look at the induced dynamics and the collection that you just chose. From that, you fix some algorithm that that produces a subgraph of the subgraph corresponding to your dynamics, okay? So each subgraph has the dynamics induced from the ambient graph, and then you want to extract corresponding to each time bin of a dynamics. You want to extract yet a smaller object, okay? And then by using some numerical or topological invariant of graphs, you can vectorize this action and produce a vector which is digestible by machine learning algorithm. Okay, so that's the idea. Now, the first question you ask yourself is, how do you select a collection of meaningful subgraphs? Okay, so you could look at the activity, and that could give you a hint, but that is going to depend on every task you're doing. And what we are looking for, being mathematicians, is something which is more objective. So we decided to look at a very standard construction, which is very well studied in combinatorics, and that of the neighborhood. And so the definition is simple. Closed neighborhood of a vertex V0, this is our V0 here, is basically the subgraph of the ambient graph generated by V0 and all its immediate neighbors. We are ignoring orientation here, so we're looking at, I mean, you can talk about in neighbors and out neighbors. We're looking at all of them, okay, all the neighbors, okay? So in every neighborhood like that has its own center, and obviously, for every graph that you're looking at, every vertex has a neighborhood. So the question remains how to choose the good ones. What does the good one even mean? But how to choose the good ones, appropriate ones. And what we did is basically the following. We looked at a bunch of topological and graphic invariants. Some of them are standard in the literature, and some of them we just invented. Okay, so I'm naming a few here. There's the clustering coefficient that is standard graph invariant. There is the transitive clustering coefficient, which we kind of we twisted the clustering coefficient a little bit and got another one which we thought was more suitable for directed graphs. There are spectral graph invariants like the Laplacian, transition probability, adjacency matrix. Look at spectral gaps and spectral radius. The next two density coefficients and normalized Betti coefficients are invariants that we invented. The Betti is topological, density is more combinatorial, and several others, quite a few others. There's an Euler characteristic there and whatnot. So we examine about 32 different parameters. And now you can take these parameters, are all numerical values. You can take these parameters and you can make an ordered list of your neurons, of your vertices, according to the order that they present. So we can look at the top 10, the top 20, the top 50, whatever you want, okay? So we look at the champions. We also looked at the ones that come from the bottom. Maybe a particular invariant will not be good for classification. So we also look from the bottom and from the top to see the results. And now, once we have this sorted list, right? We have a sorted list. We looked at the neighborhoods. We looked at the neighborhoods of each one of the vertices in the sorted, say the top 50 neurons. We looked at the neighborhoods. We constructed a directed flood complex of the neighborhood. So we have 50 graphs for every parameter. We have 50 graphs and 50 topological spaces that correspond to it, for which we can now look at the binary dynamics. We can take several time bins for each stimulus, get the resulting in the induced subgraphs of the subgraphs, okay, of the neighborhoods, in subgraphs of the neighborhoods, and to those we then apply again the same topological invariance. So for every topological or graph invariant, we have a sorted list, and for each one of those, we have then a vector, which means the values that the whole list of topological invariants assigns to them. That's the way we vectorize the data. Okay. So, for instance, if you had a neighborhood like this, and during a certain simulation, so a certain time being, only the neurons which are in green fired, we have this subgraph in green, and that subgraph you can compute whatever you want for, and that gives you a numerical value. So that is what is used to create the vector. Okay. All that half makes sense. I'm going pretty fast because of time, but that's the idea. Right. So we get a matrix now. For every pair of parameters from our 32 parameters, for every pair of parameters, we get a matrix which depends on both of them, okay, both parameters, and it depends on the stimulus that was injected, the period that we are examining. So the stimulus that was injected, and the resulting numbers, okay? So we have time bins and time bins. We have 50 champions. In our case, it was just 50, and we get that matrix. This is our vector. That's what we're trying to classify. And so, to summarize, the data that we get depends on the microcircuit we use, both parameters, the choice of time intervals and number of time bins, and the stimulus. And now we take this 60% of the data to train and 40% to validate. And these are the results. So what you see here in these two heat diagrams is at the bottom, and I hope you can see this, I hope it's big enough to see, you see a list of some of the parameters we used, the ones that were more successful than others. And then exactly the same list going from top to bottom here, which are the parameters in a way that we use them to featureize, to vectorize the data, okay? And the combination of the classification accuracy of the support vector machine. And so this is on the left, you see the highest value of the selection parameters, and on the right is the lowest value of the selection parameter. And you see that there is quite a marked difference. Although, if you now look closely at the numbers, you see that we got, this is the highest result. We got 88% classification accuracy, which is quite a bit more than the 12.5% you would expect from random, using the Chang-Laplacian spectral radius of the neighborhoods as a selection parameter, and the size, just the number of neurons that fired in each time bin, as the vectorizing parameter. Whereas if you look at the bottom classification, then Euler characteristic is the champion as a selection parameter. The lower Euler characteristic, the better, okay? But size, again, the number of neurons that fired in a time bin, is what is giving you the best classification accuracy. In general, you see that the size, number of neurons that fired, and Euler characteristic are the best classifiers, the best vectorizing parameters in both cases. And this is just another picture of the same one that you saw on the left there, just showing that the Chang-Laplacian spectral radius and size give the best classification, 88%. Okay.
Excuse me, could I just ask, what is the Chang-Laplacian?
The Chang-Laplacian, there is Fan Chang came up with a Laplacian matrix for directed graphs. It requires that the directed graph is strongly connected. And it's I mean, I cannot really repeat the definition here. It is quite involved, but in her book, you'll find the definition.
Okay, because so they're normalized and unnormalized Laplacians.
Yeah. No, this is, I mean, I only know one definition there, so I'm not sure that normalized is not normalized.
Okay, I'll look it up. Thank you.
But look it up. I mean, that was one of the more challenging things to compute for us because of the size of the project. But yeah, but it's there. The formulas are there. Okay. So one thing that we observed, one idea, one obvious idea, was to try and just choose neurons and look at the neighborhoods. And to our surprise, we saw is actually the results are not so bad. Okay, they're not so bad. We get, as you can see here, these are the feature parameters. Okay, these are the feature parameters that we are looking at, and then you can see what the behavior is with respect to random of neighborhoods. The former. Okay. On the other hand, the other thing to observe is that when you choose neighborhood random, then what you get is much larger error bar. So it's much more, but you still get high classification accuracy nonetheless. As you can see, where is our champion? Our champion is here, right? Our champion is here, and you have a very small error bar for the actual, chunk Laplacian, and a much larger error bar for random. Another experiment, we did 5 experiments altogether. Another experiment that we did is we just take the activity and shuffle it in various ways, and you can see again that this is what you see here in pink is the best results we got for each selection parameter, and down at the bottom in various colors you can see shuffled activity with respect to some of the better selection parameters, but not the activity is shuffled. And as you shuffle the activity, you see a significant drop in accuracy. Okay. All right. So we wanted further validation, so to know whether how much our work is dependent on the fact that we're using Blue Brain project, Bluebench project data, etc., etc. I wanted to do something else. So we looked at a system called NEST. NEST is, again, a system of spiking neurons, but very simplified, and it allows you great flexibility to design your own networks as you wish, right? And then introduce noise, modulate your activity by various ways, etc., etc. And then read out the outcome in a very straightforward way. So we designed Erdős-Renyi random graphs on 1,000 vertices with various densities. Okay, and then we introduce again 8 distinct stimuli by innervating 100 neurons randomly selected, and then repeated 500 times, each time being against 200 milliseconds, and some randomness, to make things more fun, some randomness was introduced. And then we did classification based on selection by the same parameters of 10, 20, or 50 neighborhoods. It's a much smaller graph. It's not 30,000, it's only 1,000. So 10, 20, or 50 neighborhoods out of them, and use the same algorithm exactly to get a classification. And so what you see here is basically our a sample of our 8 different input stimuli. Okay, on one hand here you see which neurons were selected to be innervated, and here is the kind of the response of the system. They look almost the same. It's really, really difficult to distinguish the responses just by eye. But again, when we apply the algorithm, we obtain a fairly good classification accuracy, not quite as good as for the Blue Brain, but fairly good. As you can see, the the cold colors are the ones which are corresponding to this experiment. The red is the previous experiment, just for comparison with the same parameter, with the same selection parameters. Okay, so the surprise here was that for best performance, if you see, it's a little difficult to distinguish these cold colors, but for best performance, we actually looked at the smallest density, okay? The smallest density with 50 neurons, the smallest density is the one that gives us the best performance, all right? So, so looking at a graph which is sparse, more or less as sparse as the blue brain one, and then looking at a selection of 50 neurons give you the best performance, which is about at the range of 80% accuracy, still much more than 12.5%. Another surprise was that some of the parameters which performed poorly for the blue brain performed very well here. So here, the champion, I believe, was this normalized Betty coefficient. And the Euler characteristic didn't do all bad at all, as you can see here, much better than what it did for the blue brain. So that is to say that the method works, but it could be that for various tasks you'll have to consider different pairs of selection and featureization parameters to get the best result. Okay, so in conclusion, what we're trying to do is to learn how the brain does, what the brain does by analyzing spikes that neurons produce. The fundamental hypothesis is that structure and function are linked, and that topological and combinatorial structure capture graph properties that can be used to decipher what the brain is doing. And finally, the final comment is that the methods are not limited to neuroscience and can be used on any binary dynamics. Anything that gives you binary dynamics, you can use that. We have, I didn't write it here, but it's in the paper. We have a whole pipeline freely available for people who want to try and use it that will compute the parameters for you, and you can run the support vector machine and get the results for your favorite binary dynamics classification task. And all that remains for me to do is to thank my collaborators. The guys on top, these young guys on top are my, well, by now former postdocs and student. Pedro is still a student, soon to graduate. And the others are already in other jobs. And then there's Michael Ryman on the left here, Catherine Hess on the right, and Henry Markram, all from Blue Brain, who kindly helped with this project. And thank you very much.
Thank you very much. Thank you very much. Everyone should feel free to unmute themselves and clap for Anne. Let me stop recording.